computer. All right, how's it going? This is our CSE 453 Computer Security Week 8 Lab Report video. It's just me and Mark today. And today we're going to be talking about our vulnerabilities. We're going to start off through and just talk briefly through our different vulnerabilities, taking turns for some of them. I'm going to start us, or Mark's going to start us off with the array index. I will get you started on that one. Take it away, Mark.
Okay, so Steve's typed in number 1 there for options. We've got the menu there. So what's going on here is we're passing in a parameter under the menu option of 1, and then it goes in and it'll either run a particular function or it won't. And so the vulnerability here is that our user input is not filtered. So we're not asserting that the user input is in between specific values that we've accounted for and then have a default. And so if you pick something, you'll see the message, you're authenticated. And if you run something outside of our options, you'll see the attempted to run exploit code, and then the little fun message, and then the crash. And so that's what we've done for our array index vulnerability.
So next is the ANSI Unicode, which was worked on by Alexander. So essentially what's happening here is we have basically some class information in the safe output, and on the unsafe one, or the exploit one, some Unicode or some Unicode characters are put in here. And so the checks that are put in place check the size of the buffer and not necessarily the number of elements that are in it. And unfortunately, with Unicode taking up more space, this can cause buffer overloads and so forth. And so that's that one. Next, we have arc injection, which is our number 3. So basically the idea is, and you can see there's obviously an error going on there, and that had to do with the program recognizing that there was an error and not wanting to proceed. But essentially you can see with the safe one, there is a function, and you'll see this obviously in our write-up, but there is a function called safe, which has the output here. This input is safe. And that output has a function call through which is overwritten on the exploit side. And when that is overwritten, it is replaced with a long or a long input, which replaces the address that's here with a different address. And I guess the program here detected that and prevented that from going forward. So essentially, it takes in what is expected to be a user input and replaces it with that address with a different address. So that's the arc input. So if we hit play again, we'll go through heap spraying.
Okay, so for heap spraying, we create and initialize a character pointer, name first, and then we immediately create a string we call password. So we assign the name, the value of team 7 for the normal function, and then we try and pass that in. And so this input collection point where the vulnerability comes in play, we will look, sorry.
Okay.
Let's see, got lost there, forgive me. So when our code is running normally, the user will input a string of characters, and we've specified that they should be less than 8. And this is passed into our heap vulnerability method. And we have made it so that there's not enough room inside of the heap vulnerability to accept this data. And so when there's the team 7, there's enough and it should run correctly. But once it gets passed in, we switch over to try and demonstrate this to what's the name of it? We call it local name is the variable that we use, and it's set up to be 8 characters instead of 16 characters. And so this is kind of how we've tried to demonstrate the heap spraying. And the problem that we kind of ran into with this is that this attack is normally associated with a shell attack. And so the OS has a lot of features on it to help prevent this. And so to do this attack, you would start your shell and you would give a command to disable the protections that the OS has built into it. And then you would use a language like Python to overrun the buffer and create kind of like a landing point for your malicious code, which would then you would plan in as many places as possible in hopes that the user would eventually click on your malicious file. And so this is what we've done to try and demonstrate that. So for the, and that's our heap spraying. So for integer overflow, we'll get that started here.
It's on.
Perfect. So for the integer overflow, we've got
Is that loaded on your end?
yep. So this is what happens when I don't have a script, sorry.
You're okay.
So for this one, we can see here that we've got Bob the Builder. We got a first name and a last name. And so what's happening in our code is we've created a limited amount of space for the first name and then the last name. And this code then puts the 2 names together to create your full name. So then you've got last name, first name, and you've got the comma in between. So what's happened is full name does not have enough room to hold the whole name if you go over its size. And so once again, we're seeing here, it says stack smashing detected and it's terminated our program. And this is the operating system of the computer actually preventing us from doing anything further. And how we did that was we input a bunch of malicious code, or it was too long, you know, we were being malicious with it. And that produced the integer overflow. And here the OS has detected that as stack smashing. And so that's how we demonstrated our integer overflow.
And the important distinction made with this one, and it won't be demonstrated with our actual stack smashing, is that there were actual commands that were placed in there in actual machine code, such as like go to 50 at 50, etc. And that, so the computer obviously noticed that and knew that these were commands that could be executed, and so prevented it from going further. Sorry, continue.
Oh, perfect. No. All right. So pointer subterfuge. Okay, so this one was a fun one. We worked all together on this one to get our project started and to try and understand our first hack here. And so what we did was we created some variables that you have a char variable, or character arrays, and they had a set size. And then to simulate the user input, we have the username and you're supposed to enter it and the password. So that creates our vulnerability point where the user can interact and push in bad code or bad input. And so to store the values that the user needs to match, we also used some constant character arrays. And so what happens is if you pick the right password or you don't go over that buffer, it'll just tell you, no, you don't have access. Or if you enter the right password, as you can see here, it says, welcome admin, you have full access. But to break the, so when you do that, that gives us our working condition. For our exploit, you can see we're outputting the extended information there. And when that happens, it actually we can actually see on the end of it, those goofy looking characters, it's starting to run into the actual stack, and you're seeing random stuff. And so we knew that we were overflowing into that. And the one thing we didn't do, I guess, was, and we were trying to figure that out, was to complete the hack, you would change the ID and somehow manipulate your access, but we were able to demonstrate the overflow. So do you have anything to add there, Steve?
No, I think you've covered it.
Okay, perfect.
So next is stack smashing. And obviously we've covered elements of stack smashing throughout up until this point. Notable, of course, that we used, this isn't real machine code, this just copied random parts of DLLs, which don't obviously have a full output, but basically we can see here, we had a basic string that was of size 16, and the first input that was put in was just the word safe, which obviously is far below our 16 limit. But when we attempted to run the exploited, a string size, and obviously this is in lieu of, say, a user input. We did this obviously rather than having to type it in manually every time. So this simulates basically a user input, and the first one being 4 characters, which is under the limit. And the second one is 80 characters with some assumedly untoward characters, and it could be actual commands for the system to do certain things, but obviously we didn't do that in this case. So you can see here, the size is 16, and you can see at the end there, as happened with the code before, we've started to see some stuff from the stack and some obviously unintended information. And so the idea here is that often what you're trying to reach is just beyond the thing that you're entering data into. So in this case, it could be the return address, or it could be something else, and you're basically overriding it with the data that is being input here. And you could put, for example, an address, which is right after those 16 characters, and that could be, for example, the return address and so forth. But yeah, a lot of these things use elements of stack smashing. And then lastly, we have vtable, and this one perhaps took us the longest. We had to go back and modify a lot of elements of our vtable, but basically we have 2 functions going on here, one called vulnerability and one called, I just called it safe class. And safe class inherits from the vulnerability class. There's some inheritance obviously with the functions, which are through polymorphism. So the first part, obviously it calls the exact same function. So we start, the code is safe. That is the safe class version of the safe function. And then I call the secure function, the hidden password cannot be displayed. And then the third function, which is to set the password, it says attempting to change the stored password to new pass. There's a variable that was passed in, unable to change the password. So that shows that the user is not able to make those changes. However, in the exploited code, we can see the code is no longer safe because we've changed the pointer address for the safe class to be the unsafe class. The hidden password is, so boom, there's our password being displayed, and that's our hidden password cannot be displayed. So this is the overwritten one, the original one. And then attempting to change the stored password to, this is the new password. And then you can see here, there's obviously, there was a bit of an overrun of the buffer there. And so when then I did a few other little things, such as, for example, showing a pointer address and things like that, vtable pointer address for both of them. But that was essentially the long and short of the vtable vulnerability. Do you have anything else to add, Mark?
I don't. I think we've pretty well covered it. So thank you for watching.
Thank you.